Hello. Hey, thanks for attending the talk this late hour of the day. So I'm going to be talking about self-compression of language models for edge inference. This is work that's been done at my company, Imagination Technologies. So Sabolch Chefalwe and James Imber have been working on this since around 2018. And then most recently, myself and Jakob Schibbel, who's in the audience now, we've been working on applying it to language models for edge inference. So maybe I'll start with a question. How many people have tried to run a local language model on their laptop or mobile phone? So we've got, I'd say 50-50 maybe now. Most people in the audience have done that. So what kind of models have you used? Olama? DeepSeek? Yes, same. If you've used Olama, you see on the GitHub page in the README how if you look at the recommendations of the RAM, the specifications for running language models, for the 32 billion parameters, you need about 32 gigs of RAM, 16 billion parameters, 16 gigs of RAM, 8 billion parameters, 8 gigs of RAM. Do you know why that might be the case? Yeah? Loading the weights. So if you can fit all of the weights on the DRAM, then you don't have to stream the weights from the hard drive or SSD. And so the bandwidth on the DRAM is larger than the bandwidth of the SSD. So if you're running by an order of magnitude, so if you're running on the DRAM, then it's quicker by an order of magnitude. And it makes language models usable, right? So that's the goal. You want to fit the weights on the memory device. They're getting larger, language models. Often the memory usage exceeds the DDR on the RAM on the device. So the goal is to try and fit as many weights as possible onto the DDR for optimal performance. Reducing the bandwidth is a priority. The reason why going from the bandwidth on different levels of that memory hierarchy, why you'd speed up inference is because LLMs in decode mode are limited by bandwidth. They're not limited by compute because there's low compute utilization and there's low data reuse. So the bandwidth is the priority. So if you reduce the bandwidth, then you increase the size of the model. Or if you reduce the bandwidth, you increase the performance in terms of inter-token latency or the text generation speed. So for edge devices like DSPs, mobile GPUs, CPUs, quantization of the entire model is necessary. The recent trend been going from 16 bits, which is what they're typically trained in, to lower numbers of bits, like 4-bit variants. And now, even ternary compression, which is where you have the weights represented in the set -1, 0, 1, is popular in large language model variants, and it's being used now in llama.cpp. So we're excited to present this method because on the task that we trained it for, on a language model task with a transformer, we have a method that beats ternary compression on a transformer language model task. So why should you care about this? Probably only if you're interested in this trade-off. So it's a trade-off between performance and accuracy. So the smaller the model, the faster it is, because if you make a smaller model smaller by 2, you reduce the bandwidth by 2, you increase the speed by 2. And with a smaller model, you might get lower accuracy because the smaller model is less capable. And conversely, if you want to improve performance in terms of, say, the loss or the performance on the downstream task, make the model larger, but you have to trade that off with having slower inference. So how do you control this trade-off? Well, we want to specify how much we care about the model being small because you might have specific hardware. And so you might say trade off a smaller model for to fit it on your device or to run it as fast as you want it on your device or use less energy. So we've got the loss here. L0 is the loss of the original model, like a language model would be a cross-entropy loss. And then we've added a term onto the loss, which is the model size Q multiplied by some weight, which is gamma, which is where you are on this line here, how much you care about accuracy versus performance. And because it's in the loss, it's optimized, so you want to get an optimal trade-off between the accuracy of the model and the model size. So to demonstrate that this method works, we've compared it to another method that uses quantization-aware training. And it's another method that puts the size of the model or an approximation of the size of the model in the loss. And we've done the same trade-off for both models. That's represented by the dots for our method and the crosses for the other method. And you can see we get a better trade-off, more optimal trade-off. We're on the Pareto front of models for this trade-off between model size and performance. So we can keep up to like 4% of the original bits of the network compared to 32-bit float, and retain virtually all of the original accuracy of the network. In this classification example for CFAR10, it's a ConvNet. And you can see that the shoulder for the drop-off in accuracy is pushed much later for our method compared to this other quantization-aware training method that also puts an approximation of the model size in the loss. We don't put an approximation, we put the model size in the loss, which is the sum of the bit widths of all the weights. Another example where this was applied in a real-world application is this challenge. It's a compression challenge for losslessly compressing 5,000 minutes of driving data to tokenize driving data. And Sebolch was able to outperform all of the other methods that were tried by using self-compression, not on, say, weights of a neural network, but you can also apply it to data distributions. So what he did was he applied self-compression using a neural network to compress the data. It's a lossy method, but storing the difference between the compressed representation and the ground truth, and that difference is easy to compress. So going into more detail, what is it? Each weight in a network is just a number with a precision given by the bit width or bit depth. We can group parameters together by bit depth. You might want to group channels of a ConvNet together or channels of a linear layer together. And self-compression treats the bit depths as learnable parameters. So then you put the model size in bytes of the model in the loss, using gamma to trade off performance for accuracy. Now, what if the bit depth goes to 0 for a group of parameters? That's nice, because then you've got sparsity, because you can just delete the bit depth parameter, you can delete the weights. Now, if you can add groups of weights to each channel, then you've got structured sparsity there, so you can delete whole channels of a network. You could also come up with elaborate designs with skip connections where you could delete whole blocks of a network. Going into more detail how it works, this is the loss function that you've seen, and a definition of Q, which is the sum of the bit widths of all of the weights. And so you can vary gamma and achieve different rates of sparsity. And this example is actually a transformer-based example using a language model, NanoGPT, Carpathy, and using a Shakespeare data set and cross-entropy loss. So varying gamma, increasing gamma leads to higher sparsity for a minimal degradation in validation loss. And you can see that increasing gamma leads to lower bits per weight. And we've got bits per weight here lower than 1.58, which is what could be achieved with ternary compression. So remember ternary compression being the set of values -1, 0, 1 that are used to represent the weights. So achieving better than that, average bits per weight for this transformer model with minimal reduction in the loss, well before that shoulder that you see in a drop-off in performance. And so this method, it outperforms not only the method that you've seen before, which was a quantization-aware training, but also post-training quantization as well. So how does it work? In PyTorch, it looks like detaching the gradient from the rounding function, and we insert quantization modules into the linear layers or anything you want to differentiate through. It could be activations as well, which is important then if you want to exploit lower precision hardware like int8 hardware. And then we use a straight-through estimator to calculate the gradients through the quantization nodes. And that straight-through estimator is detaching the gradient from the rounding function in Torch. To give you some visualizations so that you can see how this method works, I've got the simplest example. I know how I said you could quantize activations as well as the weights. Well, this is an activation. So this is a data distribution. It's a one-dimensional data distribution. It's the normal distribution. And so we're going to take samples from this data distribution, and then the loss is the difference between the quantized value, which are the red bins, and the true value. And you can use an L1 or L2 loss. But then we've got the size that is used to compress the data, so the number of bits. And you can see this is quite a large number of bits. We start with a large number of bits and train it, and during training, the bit depth is a trainable parameter, and it gets smaller. So here, we've reached the optimal trade-off between the loss due to quantization and the size that's used to represent the data. So we've compressed this data distribution, and it's found an optimal point where the outliers of the distribution are represented by the outer red dots. Most of the red dots are in the middle, where most of the data distribution lies. Now, making that example a little bit more complicated, we've got a vector, not a single random variable, but multivariate data distribution. And similar to the compression challenge, we're using a neural network with some hidden layers to compress this data distribution. And so the question is, what's the smallest number of intermediate dimensions, that number of hidden layers that we need to be able to reconstruct the input at the output? Now, of course, the network doesn't know how big the input vector is going to be. But we know the answer is 3. But let's see if self-compression can pick out 3 non-redundant channels and make all of the other channels redundant. So that's exactly what's happened, and the network has self-pruned and achieved sparsity. Now, this same sparsity can be used to not only speed up through reducing bandwidth, but actually reducing compute as well, especially in data parallel, massively parallel situations like computer vision problems, where you're not bandwidth limited, but you're compute limited. That would be incredibly useful. So taking that idea further, we're now going to compress a network and sparsify it and delete channels. So we'll allow the network to do its own hyperparameter exploration of the space of architectures. So I'll play that again. So I'm going to label the bit depth of all of the layers with a color, and the red end of the spectrum is a high bit depth starting with 8, and the darker end of the spectrum, the blues, is a low bit depth going to 0 when the color is black. So this is a classification network being sparsified, and we're going to drop the input and output channels, which are paired together when the bit depths go to 0. Oh. There we go. So that's during training, that's during self-compression. And so it's reached convergence when the trade-off between model size and accuracy has been reached. And you can see the darker areas are where whole channels have been dropped. Back to the language model example, I wanted to show you the shoulder of the drop-off with accuracy when the compression gets too large. So we're doing over compression, reducing the bits per weight below this value of about 1.5 by varying gamma up to a larger number. But if you take gamma as 0, then you're not going to do any compression at all, and you retain the full accuracy that you'd be able to achieve during normal training. So in that way, you're kind of replacing a lot of different hyperparameters of, in language models, you might see that earlier layers, earlier blocks in like a multi-head attention are more important, represent more information in their features than later blocks. So you might use a higher bit depth in the earlier blocks of a transformer compared to the later blocks. But if you let the network decide by training for the model size, you replace all of the hyperparameters that you need to express that network with different bit depths over the different blocks with just one global hyperparameter, which is gamma. So minimal exploration is needed of the architecture space or the bit depths to train it to, and you can achieve really impressive compression rates by doing this. Now, the same experiment, but I'm looking at sparsity percentage, where we've dropped the channels that are going to 0 bit depth, and just to map the loss values to the sparsity percentage. So let's look at the third from the right, where you've got a gamma of 0.1, achieving a sparsity percentage between 20 and 30%. So if you're compute limited, then that's a 20-30% increase in performance. But also, by reducing the bit depth of the weights, you've compressed the model and you've sped up inference as well. So if you're interested in how to implement this in PyTorch, here is what the quantization node looks like, which you just insert on your activations and on your weight blocks. Most of the weights, most of the size of a language model, like 90%, is in the linear layers in the attention blocks rather than the embeddings. So you might focus on compressing those blocks, but you just, to that weight tensor, apply a quantization node before and then after the activations, and that would allow you to take advantage of lower precision hardware as well, because you might reduce all of the bit depths to a certain value of a fixed point precision representation, such as int8 or int4, and that would allow you to do all the computations in this arithmetic, which has a low precision and could achieve higher bandwidths. So what are the advantages for edge inference applications? That it works across all devices, remove entire channels that drop to 0 bits during training, achieve sparsity which can be exploited on any device, whether using CPU, GPU, DSP, or NPU. And also decreasing the bandwidth required to run a certain size model, or increasing the size of the model you can run on your edge device. That's important because neural shaders need to be real-time fast in gaming, and then vision networks in automotive applications need to be responsive. You might want to train large models and accelerate large network inference in Gen AI, and when LLMs generate tokens on edge devices, their performance is limited by bandwidth, as I've talked in detail about. Finally, video generation can be accelerated by reducing channel removal. And then with advantages, there are disadvantages. It takes longer to train, so what you might want to do is start by training a normal model without quantization-aware training, and then turn on quantization-aware training once you've reached an optimal model. And that's one of the easy tricks that you can use to improve the training and avoid over-quantization and poor accuracy. So if you're interested, come and talk to us, and send James Imber at imaginationtech.com an email. There's a blog on our website which has been released within the past couple of hours on squishing neural network models by Jakob Schibbel. And yeah, come and talk. Thanks very much.